Today in class, we worked on task 8.9, how would you want to be paid? In this task, we compared linear, exponential, and quadratic rates of change over time to see which grew faster. In modules 1 and 2, we looked at comparing exponential and linear functions, and we found that exponential functions always grew faster over time. And in today's task, we added in the third type of function that we study in Math 1, which is the quadratic functions. In the Ready section of the homework, we're reviewing data and statistics work in preparation for Module 9. In this section, you're given a scenario where Jason wants to compare the heights of his favorite basketball and soccer teams. The first problem asks you to create a graphical display for each set of data. And just to review, some of the different graphical displays that you could choose from are a histogram, a box and whisker plot, or a dot plot. Next, it asks you to find the mean, median, mode, and range for each data set. Remember, the mean is the average. We find that by adding up all the data points and dividing by however many data points we had. For the median, we have to first order the data from least to greatest, and then we select the middle number. If we have an even number of data, we select the two middle numbers and find the average or the mean of those two numbers by adding them together and dividing by 2. The mode is the data point that occurs most often in the data set. And we find the range by subtracting the lowest piece of data from the highest piece of data, or the minimum from the maximum. In the set portion of your homework, you're going to be comparing linear, exponential, and quadratic functions. The first problem asks you to determine which type of function, linear, exponential, or quadratic, each table is representing. We know that linear functions have a common difference. That means that if the x values are changing by 1, then the y values all need to change by a common difference as well. In this case, each y value is also increasing by 1. For exponential functions, they have a multiplying pattern or a common ratio. So in this case, each of our x values is increasing by 1, and each of our y values is doubling. So we're multiplying by 2. The common ratio is 2. And finally, in a quadratic function, we know that if we look at the second difference, that has to be common. So in this case, each of our x values is increasing by 1. Our y values, first difference, is not the same. It is not common. But when we take the difference of those first differences, or the second difference, it is common, and it is positive 1. In this example, we're given 3 different equations, asked to identify whether each one is quadratic, linear, or exponential, and then we're given a value for x to substitute into each of the equations to determine which has the greatest value. We can see that the first equation or function is quadratic because the first term is exponential, the second term is linear, and the third term is constant. In this case, that would be 0. We know that linear functions do not have the exponential term. They have the linear term and the constant, and the exponential function in the middle, g of x equals 3 to the x power, simply has the exponential term. In this example, we are asked to replace the x variables with the value of 1 to determine which equation has the greatest value. You can see when we replace the x with the value of 1 in the linear function, f of 1 would equal 7. In the exponential function, g of 1 would equal 3. And in the quadratic function, h of 1 would equal 4. We can see that with a low x value, the linear function actually has the greatest value. In this example, x has a value of 10. When we replace the x variables with the value of 10, we see that in the linear function, f of 10 equals 52. In the exponential function, g of 10 has a value of 59,049, and in the quadratic function, h of 10 has a value of 130. Notice that as the x value increases, as in this example, the exponential function now has the greatest value. The Go section is asking you to identify the initial value and the average rate of change for linear and exponential functions in different forms. Recall that the average rate of change is also the slope, which we find by dividing the change in the y values by the change in the x values. In this example, we're given a graph and we're asked to find the initial value. If we take a closer look at the graph, the initial value is the y value when the x value is 0. And we can see that here, when x is 0, y is 1. Next, we're asked to find the average rate of change on the interval 1 to 2. So we're looking for the change in the first 2 points, when x is 1 and when x is 2. Even though this is an exponential function, we're looking for the slope of the line that would connect those 2 points. And we learned in a previous module that that's called the secant line. We can see that our x values are increasing by 1 and our y values are increasing by 2. So the change in the y values, which is 2, divided by the change in the x values, which is 1, gives us an average rate of change of 2. And finally, our last example, the average rate of change from the interval 3 to 4. So again, we're looking at the 2 points that are located when x is 3 and when x is 4. So if we were to draw a straight line connecting those 2 points, the point 38 and the point 416, we're trying to find the slope of that line. We can see that it's rising 8 and running 1, or the change in the y values is 8 divided by the change in the x values, which is 1.